permission. If you have the floor, so just speak loudly and quiet. You can have the floor more than one time. The moderator will keep the timing strict. The moderator will be me, so I will try to keep the time strict. Use the chat for questions. The question will be then brought forward to the moderator. Please make use of the survey for feedback on agenda page, and you can comment on Twitter or send feedback to the e-IRG secretariat. e-IRG is a member state body. The vision of e-IRG is to facilitate the integration in the area of European infrastructures and connected services within and between member states at the European level and globally. The mission is to support a coherent, innovative, and strategic European infrastructure policymaking and to enhance development of convergence and sustainable e-infrastructure services. We have prepared during the last years some documents. We published them. I'd like to remind some of them. For example, the infrastructure commons that paved the way to the IRG. It was published in 2012. Then we continued our reflections, and we stressed the need for infrastructures coordination at the national level and strong national building blocks. And we published a roadmap 2016. Then 3 years later, we published the results of our reflections concerning the role of the national nodes in the implementation of the infrastructure commons and in the instantiation as the European Open Science Cloud. The last paper we are preparing, it will be finished by the end of this year, is a white paper. The first part was published last year. The second part is going to be published at the beginning of the next year, and will have the name White Paper 2022. I'd like to thank again our colleagues who prepared this program under the chair of Jan Gruntorad of Czesnet, Czech Republic, Volker Beckmann, Panos Agirakis, Stefan Hanslik, Marko Bonac, and then the colleagues from the support office, Jan Vibelitz, Fotis Karayannis, Michael Maragakis, and Bernd Sauruga. My colleague Xavier, who was supposed to moderate this session, is ill, and therefore I will moderate the session now. The context of this session is related to this question. What are possible approaches of interlinking and interconnecting services, workflows, and outputs in evolving open and fast ecosystems, focusing on automations and machine actionability? The speakers are Larry Lenham, who joins us from the US via online, then Hans Pfeifenberger, Gabriela Machias, Markus Stocker, Thomas Mixa, and Natalia Manola. I'd like to introduce and then give the floor to Larry. Larry Lenham is Director of Information Management Technology and Senior Vice President at the Corporation for National Research Initiatives, where he works with organizations in both the public and private sector to develop experimental and pilot applications of advanced networking and information management technologies. Larry's current work is focused on Siena-Rise digital object architecture, which is based on the concept of the digital object, a uniform approach to representing digital information across computing and application environments, both now and into the future. So Larry, welcome. The floor is yours.
Okay, thank you, Paolo. So do I now share my screen? See if that works. Does that look like it should?
Okay.
Yes, okay. And Paolo, remind me, I have 15 minutes, is that correct?
This is correct. So take your time.
Okay, very good, thank you. So thank you, Paolo, and thank you for inviting me to give this talk. I wish I was there. I apologize for not being there, but it was not possible. So thank you for your indulgence, letting me give this presentation remotely. The topic of the talk is the FAIR Digital Object Forum conference, first international conference, which was held last October in Leiden. The program co-chairs were Peter Wittenberg, Paolo Brudoni, and myself. I will describe the FAIR outcomes, if you will, of the conference, give you some numbers, and then how you can find out more if you wish, and also the context of it. Why does this organization exist? What did we think we were doing? And where are we going? So we begin with the numbers. So this was held last October. We had 240 attendees, 175 institutions, 30 countries. Working groups, which had been meeting virtually for a year at least, finally met in person for the first time. There were 3 themes to the conference: the research, technology, and policy. We had panel discussions with a number of international experts. We had technical presentations, abstracts published, including posters. All of this was recorded. It's all available on YouTube. You can find the link at the FDO website, fairdo.org. It was 2.5 days. If you want to watch the conference, it'll take more than 2.5 days to watch it because we had parallel sessions. It was closed with the Leiden Declaration, which is still out there available for signature on that fairdo.org. It's fairly generic. It lays out goals and a commitment to continuing action. A lot of people signed it, probably more will come. The program committee, at any rate, steering committee and the program committee regarded this conference as a success. And it was not without its detractors, which I'll get to at the end, but it felt like a good conference to us. Fair amount of enthusiasm, and there's clearly traction. And the second conference is in the planning stage. I used to work for DARPA, and one of the things I learned at DARPA was that failure is easy. You just drop that idea and move on to the next one. Success is hard. We've now gotten to the hard part of the FAIR Digital Object effort, because we now have to figure out how to keep it going forward. So where did this organization come from? Well, you all know, I won't go into FAIR, which I assume everyone in the room is very familiar with. And digital object architecture was seen by some as a promising implementation pathway. So as you know, FAIR is a set of principles, an attempt to get the vast amounts of data out there accessible to machines as well as people in some sort of interoperable way. I should mention, when I was looking at Paolo's introductory slides, that I don't know if FDO is the answer to the e-IRG questions, but it's certainly on topic. We address those questions. So the people who saw there's a possible synergy between this architecture, which I represent, and FAIR, organized a meeting in Paris, fall of 2019, following a Research Data Alliance meeting in Helsinki, as I recall, and issued a joint statement on the FAIR Digital Object Framework. That was the beginning of the organization. The goal was to coordinate efforts, encourage use, come to as broad a definition of interoperability and approach interoperability as we could. Then the pandemic hit almost immediately and things went quiet. And we recently re-energized the group and accelerated. Steering committee and working groups were formed, working since at least 2021. And we have 4 co-chairs, 2 from the US and 2 from Europe. Their names are there. So where are we? Well, we have 5 working groups. We have sort of an internet rough consensus and running code approach to this. We know we can't define everything in advance without trying it out. We know basically where we're going, which I'll get to in a minute. We have some recommendations and specifications open for public comment. They'll be out there on that fairdo.org website. We have a memorandum of understanding with the German ISO branch, if you will, DIN. They hope to take our proto recommendations and specifications, if you will, and turn them into real specifications. And there are funding applications in on both sides of the Atlantic. So far, this has been all volunteer. So everyone involved still has a day job. We put the effort into it we can. We hope there'll be some money coming. It looks promising in both cases. There's a steering committee, now up to 20 people, and ongoing discussions with multiple related organizations for joint efforts. We've had some public forums and outreach events. We had, for example, a 90-minute Q&A session a few days ago on Zoom, and it went fairly well. I noticed some of the people in attendance were also there. It's possible to join as an institutional affiliation. There's no cost to that. And we have an open mailing list. That is, we're doing our best to be as transparent as possible, given the volunteer effort. So what was the source of this idea that digital object architecture would add to findable, accessible, interoperable, and reusable principles? Our basic approach is to add a level of abstraction to current information management system and methods to create a set of persistently identified and uniformly addressable digital objects. This idea of a level of abstraction is not new. We did not invent it. The history of computing basically proceeds with this. And in fact, the history of information management in general. Accounting is an abstraction. Instead of having a herd of cows, you have little numbers or little symbols of what the cows are. Certainly through the years, computing has evolved in that way. There's a sort of a joke that every problem in computing is solved by adding a level of indirection. So our approach to that in terms of information management is every object can be treated the same, regardless of information content. Every object has a globally unique and actionable identifier. Every object is typed. Every object has tightly associated metadata. An important feature is every object has a queryable set of operations that can be requested of it. And every object can be addressed via a known protocol. There may be more than one of these. In the end, there is one now called the Digital Object Interface Protocol. This, the idea of treating every object the same, regardless of content, has parallels that you are familiar with and use every day. The internet moves packets. The basic technology of the internet is just to move packets from one place to another. What happens to those packets is not the business of the network engineers. The network engineers make it, and they've achieved tremendous efficiency because of this. They don't worry what's inside the packets. That's the worry of the people who receive the packets on the other end. The file system you use every day is much the same. The people who design file systems and storage devices don't care about what's in the files that they're storing. That's up to the application builders. So that sort of segmentation, that sort of level of abstraction is what allows progress in technology of this sort. And that's what we're looking for here. This is an illustration. This comes from a biodiversity group that I'm working with that attempts to illustrate this. So at the bottom row, where you see some abstractions of storage devices and so on, you have existing collections of information. And notice that below that, we have existing services to continue. This is how are we going to implement this? How are we going to add this level of abstraction? We're not going to replace all the current storage mechanisms and repositories. That's out of the question. Nor are we going to try and replace those existing services. What we're going to do, and that's the little gear layer on top of that, this layer here, we're going to introduce a mapping function where we take this data and normalize it in database terms anyway. We normalize it into a, form that can be uniformly addressed, moved around, think files, packets, etc. And these digital objects, which in the case of biodiversity are called digital specimens, each one representing a physical specimen held in a collection somewhere, also link to related data sources. So you have one place to go and find out about this entity. And those data resources can, of course, be literature, DNA information, related resources, and so on. And these objects can be aggregated into collections of objects. And those objects in those collections can be addressed by autonomous processes, individual researchers, and other infrastructures. Here's an example, again, in the biodiversity world. This is a virtual object. That is, these pieces of information may be spread around, just like a file on your hard disk is actually in many places. But you can address it. The technology allows you to address it as a unit. In the upper left, you'll see an identifier. There's a type. There's some metadata. There's a local identifier. That is, this is from a museum that had identifiers. So, but it's not globally unique identifier, so you add one of those on top of it. And then you have links to other things like the DNA data and where it was collected and so on. All right, so that's the basic approach. Where are we going? What is needed to get there? Where are we now? And how do we get there from here? So this first bullet is my wording. I think it's right. I don't know that everyone would agree with it, but we're after a global interoperable data space in which previously unencountered data objects can be interpreted, understood, and operated on by autonomous agents. How long it will take us to get there, I don't know. That is highly ambitious. We want a world of data that machines can navigate because people cannot. There's too much. There's too much research and commercial data for human beings to exploit. No human being or collection of human beings can look at billions. In the biodiversity world, for example, there are billions of these specimens. How do we find a spread across the world and having been collected over centuries? How do we figure out the connections between those? We also need interoperability across time. So current data has future value. All of you people in the audience who have data of some kind, or responsible for it, or curated, or know people who do, much of that data will be of value in 50 years or 100 years, maybe of more value than it is today. Think of climate data. You cannot tell me what the computing environment in any detail will be like 50 or 100 years from now. It's unimaginable. So you have to have as abstract a notion of managing this data as possible. And our abstract notion is it's got an identifier, you can address it. It's got a set of operations. You can say, give me the data, turn it inside out, etc. And it has a way to talk to it. That's to us the minimal way to approach this. As the last three sub-bullets, we need minimal specifications or various software components and network infrastructures when brought together create the required environment. Think of the internet. At the very lowest level of moving packets around, it's a very small set of specifications. Everything is built on top of that. We need a test bed because we don't know how this is going to work yet exactly to test the interoperability, and we need maximum flexibility. This is another thing I've learned over the years. You need as few features as possible while still maintaining the needed functionality. So you have to define the functionality that you need. That's the FAIR principles, we think. And we'll try and come up with a similar set for FAIR digital objects. We're not quite there yet. All right, there's a bit of a repeat. Persistent identification is what we need. You can't manage objects if you can't reference them. We need typing if you're going to ask machines to look at entities and decide what to do with them or help you decide what to do with them. The machines need some clues. What kind of object is this? That will vary by domain. There's no universal set of attributes for every digital object. You need an interface, a way to talk to them, and you need a test bed. we can divide this into basically 3 phases. I think I'm coming to the end of the talk, and I think I'm coming to the end of my time. There was preliminary work out of various organizations, Research Data Alliance, organization called DANA, which manages the handle system, among other things. EOSC, CODATA. There is now a digital object fabric interest group in RDA. We ramped up from those beginnings, working groups, specs, publication, new organization, and we had the conference. What are we going to do in the future? We're going to try and bring in existing practices. We're going to try and come up with funding. That third bullet there under FDO Future is an important one. And we appreciate advice on this. Do we need a new organization? Should it be part of another organization? We don't know that yet. We need to use the resources we have in an optimal fashion. Need to finish the specifications, perhaps in cooperation with DIN, I hope so. And we need test beds and implementations. All right, finally, how did anyone not like FDO 22? Yes, and the primary and often repeated criticism, both during and following the conference, was lack of transparency. The steering committee, of which I am part, agrees with this criticism, but it's not our intent. It's lack of capacity. Again, all volunteer effort. We had overwhelming interest, lots of working group activity, early implementations demo, all needing greater organization, easy accessibility. As a trivial example of where we are, I showed you 4 co-chairs earlier. I know who they are because I'm part of the steering committee. You can't find that out at the website. We're struggling to get all this information out there. And that's the end of my talk. And I will stop screen sharing.
Thank you very much, Larry. It was very useful. Please stay online because of the panel discussion. We are gathering questions or topics, and then we will discuss them during the panel. I'd like now to invite the next speaker to the floor. The next speaker is Hans Pfeifenberger, who is an independent consultant on scientific data infrastructures and policies. Until recently, he led the IT infrastructure department of the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research in Germany. Hans has been chair of the Helmholtz Open Science Working Group, has advised the knowledge exchange and chaired the Science Europe Policy Working Group on access to research data. He's also founder and now member of the advisory board of the journal Earth System Science Data, an early data journal providing quality assurance to publish data through peer review. In his presentation, Hans will talk about experiences with the Earth System Science Data. So Hans, the floor is yours.
Thank you, Paolo. I must make a full disclosure here. I'm here funded by Copernicus, the publisher, which is legally a commercial publisher, but actually more or less working on the public good. Definitely not a profit margin of 40% like Elsevier or so. Thank you for the introduction anyway. And I will, well, if it actually works, it doesn't. Yes, I will rush you through something like 17 years of linking. I hope so. And I will, but I will focus on the global carbon budget as an example and the future. I hope so. So 17 years ago or so, my colleague and I presented a vision of linking, which you can see here, that was mainly about the relationships between text, that is research articles, data, and people, and their projects and expeditions and so on ships, which was our main concern at that time. At that time, oops. We already had the first DOIs for, no, thank you, back. first DOIs for data. And but concerning all those relationships, they were captured mostly in articles, that is in textual descriptions, more or less roughly. The notion of a data author or creator of data was not very much state of the art at that time. And all the description of data in articles were rather hush-hush. And that led us to think about the founding of a data journal where the description would be more thorough. And by we, I mean Dave Carlson and myself. Dave was then the program manager of the International Polar Year 2007-2008, which was supposed to produce a data legacy for decades and centuries, which is very important in particular to polar research. And we both were, well, skeptical about the state of the art with data. But regarding the journal itself, it had to provide mostly and most importantly peer-reviewed data, and it should provide recognition to data creators, authors. That is actually their reward for describing data, for publishing data, and so on. Sorry. Oh. Where should I point this? Doesn't seem to work. Next slide, please. Thank you. Here you see another kind of linking ecosystem, which you probably don't know, or many of you probably don't know. It's the linking ecosystem of publishers, which is there to serve the need to find and make articles available and to provide recognition and reward to authors. For example, all articles from all Copernicus journals are preserved and backed up in these services and Circle, Clocks, and Portico, in case the publisher should go bankrupt. And these, yeah. And then there are services for indexing, and the most important ones for the users are actually Clarivate, the Science Citation Index, which computes the Hirsch Index for people, and of course Google Scholar. Many of you may not know the background activity of Crossref. You should look into that if you don't know it, because there needs to be something like that for data. Perhaps it's DataCite. Some years later, 8 years ago, actually, I presented this one just to show that there was already an environment of identifiers present then to do all that linking, not just data DOIs, but ORCIDs and FundRef identifiers and so on. There were even now here prevented from seeing identifiers for samples, physical samples that is, and identifiers for software provided through the Nodo, where you could dump your GitHub software or software from GitHub. What we could do with our internal system with all that linking is of course very funny, but you can't do it in the world because not all objects are linked so very well as in our internal systems. So now for this concrete examples of actually a series of articles about the global carbon budget. In 2012, there was a trifecta of digital objects, namely an article in Nature Climate Change, the challenge to keep global warming below 2 degrees Celsius. You see, this is still a question of interest today. And that was linked, published on the 2nd of December 2012, right before one of the Conference of Parties, which you probably have heard about this year again. And that was linked to the article in ESSD about the global carbon budget 59 to 2011. Oops, and that was linked to a data set hosted by the US Carbon Dioxide Information and Analysis Center, CDIAC. The fun thing about that article, or actually that series of articles which emerged then, every year a new budget, was in 2011, we had to convince CDIAC that data sets should have a DOI. They had to build the system for that in order to publish our data set here. And good enough we did that, because in 2017, CDIAC was shut down by the US government. The good news is all the DOIs still resolve, while most of the data have been moved from Oak Ridge National Laboratory to Lawrence Berkeley. The not so good news is at Lawrence Berkeley, most of the DOIs of that period resolved to just one page holding links to a number of the budgets. They have degraded the metadata. In particular, they have no authorship data at this rescue site, data authorship. They provide just two, let's say, random names there. From 2017 on, data have been hosted by GCOS, which is the Global Carbon Observatory System or something, which is an S3 ERIC. And so hopefully it will live for some time. Mind you that this data will be of interest in decades to come, maybe centuries, if we survive. And of course, the DOIs resolve. They have good referencing, like referencing to the associated ESSD articles from the data set. But I wonder, I didn't test it or don't know it, but I wonder if these pages are actually machine readable. And unfortunately, as a minor concern of, I think, users, if you go from the 2017 budget to the data set at GCOS, you wouldn't see that there are new budgets like 18, 19, 20, 21. There is no link forwards to more or most recent versions of the data sets. Another funny thing about the 2012 trifecta was that climate change, nature climate change demanded that we don't publish the ESSD article before theirs, because it was time for the conference of parties. And so, while Copernicus, the publisher, couldn't do it any other way than to halt their engine, their publishing engine, for a day to exactly meet the embargo time. And there had to be personal communication between the Nature Climate Change editor, Copernicus technical department, and myself to make sure that the mutual citations actually were correct and complete, like with the DOIs. Speaking about today, in ESSD, there are still, when articles are submitted, 20% of them come without a final DOI for the data. It's not just ready. They need to have something like a review token or similar so that reviewers can actually do the review on the data itself. But so many, and the executive editor said 50% or so, that was his belly feeling, meanwhile are delivered or hosted by Zenodo, just probably because it's so easy to dump your data, or sorry, to upload your data set to Zenodo, put a minimum of metadata there, and you immediately get a DOI. In most cases, that will not be, well, seen well by people doing metadata for data sets in earth science, but this is how it is. And it can be understood because one of the major disciplinary data repositories, which I will not name here, and which was used by most of the authors in the first years, now has a one-year black backlog. That is, if you submit a data set there, you will have your DOI in a 1 year or so, because they have to manually do all the metadata in order to have rich metadata. So now about the future. I will give you the future in terms of the executable article. That's my vision, or the vision of many, I guess. And you will probably guess what an executable article or an executable research compendium might be, and what is required to make that possible. Just to state the fact about today, you see this table here from our journal report. Of course, 100% of articles in ESSD have an associated data set, and already 17% have code associated with it. I could also say only 17%. And 93% have ORCIDs, but not 100%. So what is demanded of e-infrastructures from the perspective of, and I say this is the most important perspective, of trustworthiness of science. Trust in science, trustworthiness of science, that is trust in the digital objects we use to convey science. And instead of analyzing this academically, I ask you very thoroughly that you should read this article, which you can see in my presentation, which will be online, I guess. So you have the citation here. This young, I guess this is a young colleague, did the excruciating work of making her paper executable, by which she had to prepare so many objects very thoroughly and link them and so on, published 2 years ago in Nature Physics Communications. And she established, I think, a benchmark for the e-infrastructure, that from a research article with one click, you can execute, for example, a Jupyter notebook with all the necessary data available to reproduce each and every step taken to arrive at a publication's conclusion, from the raw data to the polished plot. And above that, it enables the possibility to extend the analysis beyond what is typically reported in a traditional publication. And I've seen other example of that executable papers where people specifically enabled the user or the reader to do something like sensitivity analysis. Vary some parameters to see if the conclusions depend on the exact value of an estimated parameter. So that is actually, as I said, this is the benchmark from our perspective, let's say, of trustworthiness, reproducibility, repeatability, etc. of science put into e-infrastructures. So my conclusions from this are, what is actually needed is an easy-to-use socio-technical framework with an emphasis on the social component, I think, to publish interlinked research objects on federated infrastructure. And this is today just a vision, I guess, which is years or decades away from becoming a reality. And this vision faces competition. We see authors in ESSD flocking to Google Earth Engine because it's so easy to use, because the data is, much of the data they need is already there, petabytes of satellite data, that is. Well, also we see that sufficient and correct, not to speak of rich metadata, is still lacking on most platforms. And I suspect that the manual creation of metadata, as we see with this disciplinary repository, may be outrun one day by artificial intelligence, something like the chat GPT, which we have heard about these last days. And to end on a sober note, even to maintain the resolving of data DOIs is still fragile, I think. So we need to make sure, the e-infrastructure needs to make sure that all these things actually fall into place, period. Thank you for your attention.
Thank you, Hans. Thank you also for the appreciation. I'd like to invite now the next speaker, Gabriela Mejias, to the floor. Gabriela is a data science community manager and leads the participation in the Fair Impact and the Fair Core for IRG projects. In her role, she also contributes to data site outreach and collaborates with the research community. She's interested in shaping a more open research in infrastructure. She will talk about connecting research with the PID graph. Gabriela, the floor is yours.
Thank you so much, and hello everyone. I'm really happy to be part of this conference, and thanks to Jan Rivalitz for the invitation to participate in the session. And I'm going to give a presentation about the PID graph developed by DataCite. So to start with, persistent identifiers can be considered as the building blocks of research infrastructure. Persistent identifier is a unique and long-lasting reference to an entity such as a publication, a data set, a researcher, and it is a machine-readable string of characters, and it needs to conform to a scheme, and unlike a URL, a PID persistently points to that specific entity over time, ensuring that it can always be found. Example of very globally adopted persistent identifiers include ORCID IDs for researchers, WAR identifiers for research organizations. WAR stands for Research Organization Registry. It's a new community initiative. And Crossref DOIs for journal articles, and DataCite DOIs for data sets. And obviously there are more persistent identifiers in the ecosystem. I've just mentioned these 4 organizations as beyond identifiers. They also provide open infrastructure, meaning open metadata, open APIs, and open documentation. And also important to say that PIDs and their associated metadata are mentioned throughout all the FAIR principle elements. They help make research data and outputs findable and accessible through this persistent identification they provide. And more important, they also improve interoperability by creating links between these different digital entities and providing context through metadata that can reference other persistent identifiers and other metadata. And also important to note that persistent identifiers also play an important role in the reusability of research data, as with this rich metadata and data provenance that is also associated to these digital objects, they allow for better understanding of research, which can then trigger more reusability. And we know that research is already and increasingly interconnected. So research already forms a graph, and persistent identifiers not only uniquely identified an institution, an author, a publication, or a data set, but the metadata of these persistent identifiers can also provide unambiguous linking between persistent identifiers for the same kind of object types, like journal articles citing other journal articles, but also they can provide linking and connections for different kind of entities. For example, linking a researcher to all the data sets they have produced. And a PID graph technology requires standard ways for exposing and discovering these connections, as well as infrastructure that makes it possible to both contribute and consume these connections. And this is what DataCite has implemented as part of the Freya project. And persistent identifiers have the potential to enable connection between entities across a research ecosystem, but metadata is what realize the true potential of persistent identifiers, as they help, they are the glue that connect these different entities and that make these connections also openly and transparently available to all. And the PID graph was developed by DataCite as part of the Freya project with funding from the European Commission. This project ran from 2017 to 2020 and is a graph of scholarly resources. And what makes this graph unique, because there are other graphs in the ecosystem, is that all these entities are identified through persistent identifiers, and the metadata of these PIDs describes connections to other PIDs. And the Freya project identified the most important use cases and standards used for the technical architecture and deployed its implementation. And this information can be explored using, for example, Jupyter notebooks. And metadata is key, is central for this to work. Metadata for digital objects can and should include connected persistent identifiers. And on this slide, you can see the relations that are part of the DataCite schema for DOIs. These relations are very important as it helps us increase our understanding of research, for example, to better understand versioning, because with this metadata, it's possible to assert that dataset 1 is a version of dataset 2. It helps us understand granularity. It's possible to describe that dataset 1 is part of dataset 2. It helps us understand who funded research. It's possible to connect this information as well to say this dataset is funded by this funder. And also it's possible to, it allows us to understand authorship, and it's possible to assert all the creators of a dataset. And DataCite provides this technology, but obviously we cannot connect research on our own. Rather, this is a community effort, thanks to the organizations that register persistent identifiers and that register and curate these relational metadata. Research becomes more discoverable, and persistent identifiers and metadata interconnected formed this PID graph. And you can see here a snapshot from earlier this year, from August. And you can see all the PIDs connected for the different entities. So 14 million researchers identified through ORCID IDs, more than 100,000 organizations identified with ROR IDs, and connected to 12 million datasets that are registered or identified with dataset DOIs. Plus information about publications, software, funders. This is just an example of a Jupyter notebook, but this graph can take different forms depending on the queries you make. And important to say that we offer open infrastructure, so this information is available to all via a GraphQL API that is open to all. And we also have a user interface connected to the PID graph that's called DataCite Commons, so that it's possible to search by work type, by researcher, by organizations, and also by repositories. And this connection is powered by Re3 data, which is the registry of research data repositories. And now I'm going to show you some examples of the kind of queries or questions that it's possible to answer with the PID graph through DataCite Commons. So one of the most basic queries is possible to search and, for example, retrieve works, in this case, data set, and you can retrieve the DOI of that data set and additional information. And it's also possible to discover how many times a data set has been cited and referenced, and also viewed and downloaded through this platform DataCite Commons. And more interesting, it's possible to discover more information like in which journal article this data set has been cited, the publication year, the licensing type. And this technology also helps increase recognition for all kinds of contributions to research. So, for example, it's possible to identify and recognize researchers and the institutions they're affiliated with. And as mentioned before, this technology is powered and leverages on existing infrastructure, so existing persistent identifiers. So it's also possible to search by ORCID ID and then retrieve and discover visualization of all the connected research outputs, so all the outputs associated to the ID. And in more granular information, you can also discover these outputs by publication year, by work type, and by licensing type. And the PID graph also allows for more complex queries. For example, I want to search all works that have been funded by a specific grant, including resource types, publication years, citations, views and downloads. And you can also see the funding organization that can be identified through a ROR identifier. So in this case, the referenced funding corresponds to the Freya project, and you can see the organization that funded it. So in this case, the European Commission with the ROR identifier. And overall, this funded is referenced by more than 160 works, and you can see the work type and the licensing types. And the good news is that this technology keeps being relevant for the community and keeps evolving, and it will be one of the 9 e-IRG core components. This work is currently being done by the FAIR Core for e-IRG project, also funded by the European Commission. The project kicked off in June this year and will expand the sources that are included in the PID graph, and will also develop a service that makes it easier for researchers and organizations to harvest this data. The requirements and specifications are currently being finalized, so hopefully next time I can share more detailed information with you. And to finish, a call, an invitation, please consider contributing to this community effort of connected research by registering persistent identifiers for your research, by promoting the use of persistent identifiers, and obviously, and very important, to curate rich metadata that includes connections with other persistent identifiers, and to make sure these connections are openly available, use PID providers that offer open metadata. And this is the end of my presentation, and I look forward to the discussion afterwards.
Gabriela, I thank you very much for these insights. And I now like to invite the next speaker, Markus Stocker, to take the floor. Markus, you lead the research group at the Leibniz Information Center for Science and Technology in Hanover. Your research interests lie on the intersection between research infrastructures and research communities, and how such infrastructure acquire, maintain, and share scientific knowledge about human and natural worlds. So we thank you for your contribution, and I give you now the floor.
Yes, thank you, Paolo, for the introduction, and also Jan for the invitation today. And I will talk a little bit about fair scientific information. So we heard of research data, and I will focus on a particular kind of research data, that is data and information in the literature, and ideas on how to apply the FAIR principle to this kind of information, and you know, the challenges along the way. And focus on a particular infrastructure that we develop at TIB, that is the Open Research Knowledge Graph. So scientific information is data. I think that's not controversial here. I have here an article, and you can see a lot of data, both in natural language text, but also in plots. We have some data points down here, and some p-values. So all this is data, relational data that is interlinked. So the p-value is an output of a t-test, and the plot here is the input data to the t-test, and you have a dependent variable here. So all this is data, and this data is not fair. So we don't really find this data. This data is not directly accessible, it's not interoperable, and it's very difficult to reuse because machines don't understand us, don't support us very well in these activities. So what we do find and access are documents, but then we need to read these documents in order to extract and reuse the information. So if you look at a particular example here in a paragraph, the authors speak of IRG binding activity having a significantly reduced reduction in failing hearts, and then they point to figure 1b. As I said before, there's a plot. This is essentially CSV data in a visual representation. And I would like to point to the p-value here as well. That is the output of the t-test, and also is there captured in a very approximate way. The only the information is here 0.001, but in fact, usually these p-values are to the power of -8, 10, 15, 50. So it would be great to actually have the accurate p-value, for instance, in systematic reviews. So what the machines should be able to consume, instead of consuming this text and this information in natural language text and images designed for humans, is maybe something like this. So we have here a student's t-test, that is a term of a particular ontology here, the ontology for biomedical investigations. They have a term for this. And they also structure these objects. It has a dependent variable that is, in this case, the iron responsive element binding, which again is a term of an ontology here, the gene ontology, has a specified input that will be the data set, the CSV that is in the paper is plotted. But of course, we can deposit this in more machine-readable form, and has a p-value as a specified output. That is again a term in the OB ontology, and here, contrary to the article, we can actually capture the actual p-value, the accurate value. So scientific, to quote here Baron Mons, a while ago, he wrote in an article that scientific writing can essentially be called information burying. What we do is we first bury information in text, and then we try to mine it again with artificial intelligence approaches, natural language processing, and this only performs very insufficiently. So we are not able to extract rich information from documents with these approaches. There is Atwood and colleagues a while ago also have noted, and in another article have noted that essentially we have failed to organize this information in a rigorous way, so that currently finding what we want and understanding what's already known is really a costly experience. And machines won't do it. So Julian Higgins and colleagues in the Cochrane handbook, they, as you know, they mine information from clinical trials. Note that although we have, of course, made improvements in machine learning, this kind of data extraction is really largely a manual process. So many communities have done for their own purposes and for a very narrow set of documents and have developed applications tailored to support a certain investigation, certain research effort. And this typically occurs also in efforts of systematic review. So teams that extract information from documents from the researcher anyway, they construct databases and they do the effort of publishing these databases, and some communities even create some services on top of this data so that the community can more easily interact with the data and maybe do even some analysis. So we have examples in invasion biology. So for instance, the high knowledge effort here represents in a network manner information about hypotheses is in invasion biology, their relationships, their support or questioning in the literature. And users can navigate that network. And that network is a product of analyzing and extracting information from hundreds of existing publications. Platzi is another example that does something similar in biodiversity. We have examples in social sciences. The Cooperation Data Bank has extracted out of about 2,000 papers here, numerous data values so that you can interrogate this database and ask questions. The air quality data collection that was conducted by Forschungszentrum Jülich has also in the context of a systematic review extract information, measurement data actually about the about various pollutants from about 150 publications, and they created also a visual interface to interact with this data. So then papers with code is another good example in machine learning. They have extracted performance measurement data for algorithms that in machine learning. And once you have a database like this, you can basically plot relatively easily things like trends, performance trends in a community for a particular problem, like object detection in images. You can see over 2 decades how the models perform, improve, hopefully, or not, or stagnate. MetaLab is another example in the cognitive sciences. And finally, I would like to highlight the Open Research Knowledge Graph as yet another effort in this domain for this problem, with an ambition to address this issue a little bit on a broader, more general scale. So these examples that I just showed you, they are very domain specific. They are tailored applications for a particular set of kind of information, let's say, for a particular kind of visualization of this information. And the Open Research Knowledge Graph tries to tackle this problem a little bit more generically. So I think the benefits are obvious. Once you have this information in databases, you can, for instance, compare this information more easily. So this is a kind of reuse here. Think of Amazon product information, right? You have here for basic reproduction of COVID, the estimates across the literature. So here you have 4 papers in the columns, and it has values, basically the estimate, and you can see more easily without having to read the papers. You can see how the value varies. You can even use this data set again and post-process it, for instance, for regional differences and so on. Or you can integrate a number of different sources here, case fatality rate, draw a mean, and basic reproduction and draw a mean. Then you can plot SARS-CoV-2 for deadliness and contagiousness on such a map, and relative to other infectious diseases. And since all this information is now in databases, you can come up with these artifacts and data products in a relatively easy, with little computation. Let's say you can connect to ORKG from things like Jupyter Notebooks, and directly read these data sets, these comparisons in ORKG into a data frame, and then you can process this data, as you know, with the full power of languages such as Python or R. Linking to what was said previously with pgraph, we can also, of course, interlink these kind of data sets, these products like ORKG comparisons in the pgraph, so we can identify these data sets. So we use DataCite for this, and interlink with the underlying literature that from which data is extracted, as an example, or do the other way around. We have an article, and you can discover that that article was used in an ORKG comparison. So given these benefits, why is most scientific information still buried in documents? And I think one of the bottlenecks is really how the problem of producing machine readable, machine actionable scientific information. And in ORKG, we pursue to this aim essentially three approaches. One is what I call the post-publication manually. So we have a relatively good interface to curate, to create this content in structured form. So it's basically key value pairs, where the value can be again a rich description of the data. So for instance, here basic reproduction number is 3.1, but that is a value that has an attached confidence interval, which is again structured. Location can be linked to things like geonames to provide further information about Lombardy. Time period the same, it has a beginning and end dates, and this interface allows you to essentially create this structured information in a manual manner. The alternative or additional approach is to do this or get support for machines, as I mentioned before, NLP, for instance. And this is also post-publication in an automated manner, or let's say trained manner, so it's not fully automated, but once you have the models, you can run them and they provide you suggestions, although this is generally very at an abstract level, and you have to always have a human curation in the loop here. A third approach is, in contrast to the post-publication approaches, we have a pre-publication approach, so fair at birth or fair by design. So we ensure that scientific information is produced machine readable, since a lot of this information is produced in computing environments using scripts in languages of Python and R. You can try to bind the production already at this stage. And here we integrate with ORKG templates. I'm showing you above some code that creates a linear mixed model fitting. You get some data output here, and then we describe this linear mixed model fitting for its input data set. That is a CSV file. The formula of the linear mixed model with response and predictor variables, and also the output data set, which is here just a variable that I'm passing down into the description of the linear mixed model fitting. And all this is then serialized into data, and this data can be submitted to a publisher, mentioned here based on a use case that we are developing Copernicus publications. These files essentially go into the review process together with the manuscript, and upon acceptance, the publisher can link the article DOI in metadata with the supplementary data to ensure that this supplementary data can be discovered by machines. And if you do that, ORKG or other systems also can simply harvest, given a DOI of the article, this content. You can see here the metadata of the article on top, the published journal, and below the so-called contribution data. So in tabs, we have different contributions of the work represented in human form in the article, but here also machine form in ORKG. And you can see here the linear mixed model fitting descriptions with the input data set linked to a node or the input model and the output data set. And this is now an ingestion into ORKG. You can see the output data set directly in ORKG. So that is because the output data set in this case is actually scientific information. It represents a table in the article. So fair scientific information, I think it's time to look at this in particular. So as a kind of research data in the literature and how to apply the FAIR principle to this kind of data. Thank you very much for your attention.
Marcus, I thank you very much for this insight on the essentials of your work. And I will now open the floor to Thomas Mixa, inviting him to for his presentation. Thomas is a senior researcher and an expert in data management and design of research data repositories. His area of expertise includes reproducibility of computational workflows, auditability, and digital preservation. He chairs the DMP Common Standards Working Group at the Research Data Alliance that works to realize machine-actionable data management plans and coordinates the deployment at major Austrian universities within the FAIR Data Austria project. So Thomas, the floor is yours.
Thank you very much. Can you hear me? Yeah. My slides are not ready yet, and I don't see them in the folder. It's because I sent them last month, I guess. But anyway, today I'm here with you to talk about machine actionable data management plans. And some of you might have seen my presentation about integrating RDM services at RDA plenaries. So I'm sorry if this is a repetition for you, but I came here because I want to talk to the research infrastructures, and in a nutshell, we need your actions to help in realizing the idea of machine actionable DMPs, because so far the discussion about the data management plans was mostly driven by funders and how can we please funder requirements. But the hypothesis we have at our working group on data management plans is that MADMPs can create benefits for everyone, for researchers, funders, but also all other stakeholders involved in this process. So the plan for today is that I want to give you a quick introduction on data management plans, what they are and what we don't like about them. And then the main part of my presentation will be explaining you what we did at RDA to come up with a concept of machine actionable data management plans. I will show you some examples and then give you some ideas of how you can use the recommendation of RDA in your infrastructures, in connecting the tools, in basically reducing the workload on your researchers and also creating benefit to other stakeholders. So to begin with, here I have collected some examples of checklists that researchers are asked by the funders when they create a data management plan. So you have here, the blue one is from Austria, from one of our agencies, and the other one is from National Science Foundation in the US. And as a researcher at the beginning of the project, usually you have to write a PDF document, 3, 4, 5, 10 pages, explaining what data you have, where you got it from, where you will keep it, what will you do with it afterwards, and so on. And in most cases, you take some tool, click through questions, and you're not really capable of answering everything because you have to be an expert on storage, on backups, on licensing, on metadata types, and so on. And many people just want to do their research. Then the result of this action is basically you submit it to the funder tells you it's okay or not, and the document is dead, yeah? So there is not much incentive for you to get it right. And we looked at RDA on what the data management could be if we make sure that we include all the right people in this process at the given moment in time, at a specific moment in time. And here you can see a typical workflow for writing a data management plan. So it always starts with a researcher providing basic information like what is the type and size of data that they are going to work with. Let's take it, I don't know, 5 gigabytes of images of Prague. And then what the researcher needs to answer writing a DMP is where this will be stored, how much it will cost, what license to give, and so on. And many of this information can be provided by systems acting on behalf of other stakeholders. And what I mean by that, so if I need to give a license to my data set I'm going to publish, I can, for example, give CC BY. And there are some studies showing that 80% of researchers don't care what the license is. They just ask the library or somebody responsible in the department to recommend the license. So if there is no special case, we can always recommend the CC BY. And if the researcher knows that they are somehow special, they have requirements, they usually know that stuff, and then they know whom to contact to discuss the licensing topics. The same is about the storage. I'm at the university. We can recommend to use one of the existing systems we have, which is compliant with GDPR, which does the backups. We don't have to even discuss these things with the researcher. We can give this recommendation, take it and use it, and you'll be fine. Yeah. So once this data management plan is created, we want to submit it to the funder. And of course, the question is how the funder is assessing the DMP. Is it still sending an attachment by mail, a PDF document, or do we send it in some way that the assessment can be automated? And basically to realize a vision in which we have the data management plans that are machine actionable, and I will show you an example later what it means, we need three things. We need well-defined RDM workflows. So we must identify who is responsible for what. So who is responsible for providing advice on licensing? Who is providing the storage? Who can discuss any ethical or legal issues? Who is expert in metadata? And things like this. Then you need the data management infrastructure, which is the second point. So basically you have to connect somehow these stakeholders, you have to make them talk to each other. And nowadays you just put some IT systems that do that. And the third thing is the common way to represent the information. So right now we have this templates, which are the PDF documents by the end of the day. And we need to have a way to represent information in DMPs that also machines can understand. And this brings me to the main topic of my talk, the common standard for machine actionable DMPs. So you can see in this slide, I have shown you two examples. In the top of the slide, you can see a traditional DMP, and in the bottom, the machine actionable DMP. Many of the tools for data management planning allow you to export the information provided, not only as a PDF, but for example, as XML or CSV or JSON. In this case, you see a part of XML. And somebody would say, yeah, this is already machine readable, machine actionable, whatever you call it here. Because I have XML, it should be fine. No, because there are some semantics missing, and the only thing we can query is, no, what is the question? What is the answer? We don't understand anything about the contents of the question or the contents of the answer without doing any text analysis. So the way to provide this information and make it more specific is how we did it in the bottom part in the machine actionable DMP, is that here it tells you explicitly that Moritz has this specific ORCID identifier, and the machine knows it's an ORCID and not something else. It tells you how to contact Moritz because there is an email provided, and it's clearly marked that Moritz is one of the contributors to this DMP, and his role in this data management plan is being the data manager. So it's in a contrast to saying, you know, Moritz from our university will take care of data management. It leaves a lot of interpretation also for humans and ambiguities compared to being specific about who is, in this case, data manager in the project. So it took us briefly 2 years to have discussions, consultations, analysis of what is needed, and we came up with an official recommendation from RDA on machine actionable DMPs. You can find it online. It's a 2-pager describing the key components that we agreed that a DMP must include or should include independent of the setting you are in. So if you are in Austria, Germany, United States, Africa, we talked about having a common set of information to represent machine actionable components. And we have adoptions from basically all of the DMP tool providers. We have some repositories implementing the recommendation. The degree to which the recommendation has been implemented also varies. So mostly the tools allows you to import or export information you provided into an MADMP. And the specification itself is hosted on GitHub, and you can see that it consists of a set of fields that we identified as necessary. There's a description of the field, and then information whether this field is obligatory or not. So for example, every DMP must have a contact person for a DMP, so that we are not having any DMPs that we don't know whom to ask for further clarifications. A disclaimer, we didn't want to make any unification on what questions researchers are asked. So it's not a questionnaire, it's not a template. This is what Science Europe was doing, this kind of alignment on what should be the templates. Most of the fields are optional because this is a technical specification. This means that if you want to use it in your own context, if you are a funder or if you are a research infrastructure, and you want to make your researchers or other stakeholders provide specific information, you can make the use of the fields mandatory, and you will still keep a connection to the standard. You will not break the standard. Relaxing the constraints would break it, but would break the compliance, but making it more fixed, it's okay. So here a more advanced example of what we can model, what we can express. So here you can see we're using a lot of DCAT specification in this part. So you can see that each data set that the data management plan describes has a title and a human readable description. So we still have to keep this narrative for people. For example, you have to sometimes explain why you decided to pick this repository or why you decide not to publish data. So we still keep these fields, but we clearly annotate them like this description field. There is also a clear specification of the format, size, and location of the data set. So we know here that it's kept on Zenodo, and Zenodo is using a DOI as a pitch system. There is a clearly defined license, in this case, CC BY license, which is referred using the URI, so the preferred way of referring to licenses. So you can follow up the link and get the text of the license. And there is also information about the starting date of this license. So in this way, you can model the embargo for data, or you can say that something is planned, for example. So that's all about the specification itself. That I'd like to show you some examples of and give you some ideas of how you can use the MADMP. So what we want to achieve with this MADMP is, I keep stressing that, make sure that we can connect the systems acting on behalf of different stakeholders. And in this way, MADMPs are the glue between these systems. So we can get some information from funders, for example, on project numbers, grant numbers, starting date. There is no need to ask this to your researchers. You can get updates from repositories about the data sets deposited. So what's the DOI? What is the quality of service of a specific service? We can talk to registries like Refree Data to get information that sometimes funders ask, like, can you please tell me, is it a domain-specific repository or not? And we can simply connect this to the registry and put it into a DMP. Same for local services you are operating. So how was the data processed? Where was it kept during the research and so on? So all these things can flow into the DMP and then can be reused by all other stakeholders that you can see here in the slide. So to give you examples so that you don't think it's just a visionary talk, but this is real, we are currently implementing, so parts of implementing it in Austria, in Vienna, at our university. Some of these parts are already implemented. Some of these should be released within the next 2 months. And that's why I have courage to talk about this. So we have a tool for data management planning. It's called DAMAP, but that's not really important for this story. So, but the central point is the data management planning tool, in which the researchers answer the questions in a traditional fashion, but we keep the information already according to the MADMP specification. and we import information from other systems. So for example, from the data repository, when a researcher decides to upload data into the repository of our university and they publish a data set, they can say, I want to report my data set for the DMP. And then this is automatically added to the DMP that this has been, this is one of the outputs produced by this project and this is stored in the DMP. We connect to the OpenAIRE knowledge graph to also look up data sets that the specific project is reusing. So the first question that researchers are usually asked, is there any existing data that you will reuse or not? And if yes, then please provide a DOI and we will look up this information in the knowledge graph to import the information about your data sets. So what is the title, what is the license, and so on. No need for you to type this. We connect to our CRIS system, so to get all the information about the grant number, about your affiliation, phone number, size of the shoe you're wearing, whatever you need to provide to the funder. And also we have a custom list of services for storage. So we recommend, please put your data to one of our storage services, because people usually then can choose from the list. I know I'm going to use OwnCloud or one of the servers, and that's how we basically improve the practice of data management. And as an outcome, we generate traditional DMP that the researchers still submit manually to the funder, because funders keep requiring PDFs, so we must render this information in a PDF. But we also have the same information available in the MA DMP as I have presented to you. And this is something that we want to put into our internal workflow. So maybe try automating the assessment and providing feedback to the researchers on how good the DMP is. Maybe you can increase the fairness of your actions before you submit to the funder. And maybe in the future, we manage to convince the funders also to receive DMPs also in the format of machine actionable DMPs and not only PDF. But this is a matter of discussions and decisions on the funders side. So if you are interested in this topic, if you are interested in machine actionable data management plans, if you think that this could be something for your infrastructure that you could contribute, you have some novel ideas for integrations, please join our group at RDA. It's open for everyone. You just go to the RDA website, find our group, DMP Commons Working Group, click join, and you are there. We have more than 250 members in our group. You can always contact me for any questions you may have about MA DMPs. In case you want to read a bit more on what we did and what we stand to, then there is this paper in the PLOS Computational Biology, where we outline the 10 principles for MA DMPs. There is a lot of overlaps with what I have heard today already. So we talk about PIDs and common models and making information easy to consume by machines and people. So this is basically what is driving what we're doing. And the second paper in the ACM transactions talks about the enterprise architecture that we have drafted for our university to show how you can embed the MA DMPs into your existing infrastructure of the university. So it is driving our developments locally within an university. So I think there are some ideas which you may borrow if you're interested. Of course, there are some more papers on this topic, but you can see it afterwards. So thank you very much for your attention, and I'm looking forward to the panel discussion.
Thank you, Tomasz. Now, Natalia, the floor is yours. Natalia Manola is a research associate in Athena Research and Innovation Center at the University of Athens, in the departments of informatics and telecommunications. She's the managing director of OpenAIRE since 2009, a pan-European e-infrastructure supporting open access to all scientific results, the coordinator of OpenMinded, an infrastructure on text and data mining, and is now involved in the implementation of ELIX, the Greek infrastructure for research. So Natalia, the floor is yours.
Okay, thank you. So it's me again after yesterday. And what I will present, oops, how can I go back, is I will try to tell you how we are approaching in open air, combining the two things that we discussed, is about the science or scientific knowledge graphs and fair machine actionable DMP. So, you know, it's a bunch of titles, all of them together. So we have two services, Argos and OpenAir Graph, and I will say, yeah, I will just try to present a more holistic view. I would just like to give the acknowledgement to the people who have helped me with this presentation and who are running the services. So I will just touch the higher level, not the very technical details. So it's Eli Papadopoulou from Athena Research Center, Paolo Manghi from CNR and OpenAir CTO, and George Kakaletris in a company that is supporting us in Argos. So the data management plans today, what we have, I think, Thomas, you picked up on a lot of things. So it's there are three things that I would like to focus on. On policy, technical, and adoption. What we have today is we have DMPs mainly pushed by funders. They're public, but I have to say that it's not easy to find them. It's not easy to assess them. Then we have rich contents in these DMPs, but this rich content is not easily understood. So, so what Thomas was saying. And then the support to the researchers on the policy side is they are unclear about the processes. They don't know where to start, where to get input, and how to use the DMPs. So DMPs are not just plans, but they are tools for management. Then on the technical side, we have now we have search and retrieve, interoperability, and semantics, but we have partially them. We don't have them. In a DMP, for example, is in the scholarly communication world, there is no research type for DMP. So this is a special thing that, you know, all the libraries or the publishers, we need to think about how to tag DMPs. Then how do we reuse the data sets, qualified references? This is still missing, and I think the key thing here with the actionable DMPs is that we need to tackle them. And then the adoption, it's about fair practices, disciplines, communities, data sharing. So we have DMPs and templates, but these templates are very horizontal, most of them. Research infrastructures are now entering the game on how to make these templates more customized and configured to their needs. But the tools and the services, they need to follow due. So how do we do that? So there are all these problems. Then the graphs. So on one side, I will talk about the DMPs, and on the other side about the graphs. What do we have today? What we have today is that we have quite a few graphs already existing, and they are graphs for different use. We saw two today, the PID graph and the open knowledge research graph. Different use, different formats, and different maturity levels. Some are big, some are smaller, some require researcher input, some are automated by publishers. What we know is we have graphs on scholarly communication, for example, the OpenAir graph that I will present, OpenAlex, but we also have the commercial ones, because the commercial databases are now moving more into the graph area. Then we have the national CRIS systems. I just put some countries there that I know that they have very good CRIS systems, where their focus is mainly on monitoring. And then we have domain discipline graphs like eBrains, ENVRI, ECRIN, where the focus is not on monitoring, but on discovery. So it seems now the scientific knowledge graph is taken up by many. So this is where do we go? Now, the challenge is that most existing graphs are looking into publications and the data from publications within the publication, so the semantics. How do we now have the graphs that they connect things like data, like software, all of these things together in a very authoritative manner? There are some semantics in place, but still many more to come, or we would like to come. Then some of these graphs, they have very specific coverage. Some are global, like OpenAlex or the OpenAIR graph, but most are specific or regional, like national or thematic. And then the key thing here is that, okay, everyone is building the graphs in their own way, but there is no connection. There are no ways on how we can interoperate. There is linked open data, but this is not something that we have taken up, and I can speak from OpenAIR, mainly because the sizes, that the volume is too big and it's not very scalable with non-commercial open source software. All of this, there is a project called SciLake, part of the EOSC suite of projects, that at least the challenges we will be looking at them, and it's starting in January, this January, with some very good computer science expertise and three communities from transport, from neurosciences, and from cancer and health and cancer. So we will look into the horizontal things of the challenges of how can we make this, especially working on OpenAIR, to make it work, and then see how it applies on specific domains. Now, I will give you our view. Is how do we view this knowledge, the scientific, the science graphs, and the DMP. So our idea is to use always end-to-end solutions, and this is what we try. I will not go over this picture, but this is an overview of the OpenAIR services. You're going to see tags in there. So what is to keep here is that how we are building or how we're integrating services in the scholarly communication field is that we have services, and then services talk to each other. So this is something very very key to our way of thinking. You will see the arrows. So I will talk about Argos and the graph, but the graph is something that is very central to our operations. So the graph is there. We have the guidelines. We have ingestions mechanisms that they talk via metadata guidelines to the graph. We have services that access the graph in order to get information. So this is, but the graph is central. In the data management plans with Argos, so I think, I will give a glimpse of what we do. So Argos is like what the tool that Thomas presented for Austria. Argos is a service from OpenAIR. It's a data management. It's a management research data management data plan service with open, fair. I will not talk about it, but the idea is that we offer it on the cloud, and people can come and they can collaborate, and they can start drafting their DMPs in this the way that Thomas described, in a machine actionable way. So we can import machine actionable data, DMPs, and we can export them. So there is from the stages of drafting and collaborating to the stages of validating, to finalize and updating. So this is a lot of work on this. Then what are the outputs and the processes? So why is it fair? So, every DMP can be published in Zenodo or can be exported, and it's findable by the OpenAIR graph through OpenAIR Explorer. We have accessible via PIDs, interoperable because we work with the RDA, the DMP common standard. We allow for it to be to having licenses. Then we have versioning, and then it's published and preserved in Zenodo as a PDF, even though it can be retrieved with APIs from Argos. Automated or semi-automated, I would say, is that while people are writing it, they are we can infer content and allocation in templates as answers. So this is, I think, what is called pre-filling. Then there is searching and publication. So all of it are all of these are features that modern, let's say, or modern or emerging DMPs have. And we know of 2 or 3 of these DMP services apart from Argos that are doing that. And I have to say, by the way, that it's a very good opportunity here, is because the people that are in the DMPs that are writing the platforms on the DMPs, they have very good collaborations and they talk to each other. And so this is I think one of the happy and successful examples in Europe where the teams can get together and they work and promote and advance their services. About Argos also, it's not just, you will see here, I cannot point, but you can see a pipeline where you can start with Argos. You have internally access to the OpenAIR graph and possibly to the e-IRG portal. Then you can do through Zenodo, you can export with machine actionable, and then we can use in monitor and explore in OpenAIR. So when a funder comes to OpenAIR and they can see, for example, one of the monitoring questions, the tracking questions that they would like to ask is, how would you, what are the DMPs produced linked to my funding? We can give this answer out of the box. Now I'm switching to scientific knowledge graphs, and I will see how we can, and I will come to the end and I will tell you how we're connecting both of them. The OpenAIR graph is what it is. We consider it to be a key global asset in the open science infrastructure. Why? Because it's inclusive, it's transparent, it's reproducible. Okay. I have just put some entities that the graph includes. So starting from the research product, which could be publication, data set, software, or anything else. And then we could expand this as we go along. This research product is linked to people, to organization, to funding, to beneficiaries. And now we are adding all these boxes. It's about the citations through open citations, usage data, APCs through open APC, services through the e-IRG portal, notebooks through collaboration with other infrastructures. So this is an open. Why? It's based on open science principles, and as OpenAIR, we couldn't do anything else, of course. It has a global coverage, and I will explain how. It's enriched by AI processing. There is a lot of AI behind it, for citation, reproducibility, fields of science, SDGs, domain-specific, AI-driven. So we extract information mainly from the papers, and then we propagate these links to other entities. We're moving now with the FAIR code for e-IRG towards a smart discovery. So how can you use a graph in order to put some recommendation systems and AI in order to allow people and researchers to have a smart discovery on the research areas. And then, of course, it's high relevance to the community. Why? Because we are now, we will be working with the research infrastructures to see how we can bind our graph with their graph. So this is in a nutshell. And again, in a nutshell, this is, the data sources. This is a lot of data sources, more than 10,000 data sources. The graph, if I can go back, there is 18 million research data. And I have to say, this is not research data. Much of it is garbage. So one of the key things that we need to work on is to see what is research data, because, for example, repositories like Figshare and many entries in Zenodo, they have these tables from publications and images, and they just name them as data sets. So what is a data set? This is something, I think, this is something that we need to enter the discussion with. We have 140 million publications linked to 3 million grants. So the numbers are good. They are impressive. It's hard to maintain and operate. And just, I will not go on this, but there are many, many data sources from tools and software, from other research graphs, from preprints, aggregators, registries. funding data, and now lately the research infrastructure catalogs and graphs that they are building. What are the challenges? Challenges, again, I will not go through that into the detail. Heterogeneity, we try to tackle this with the guidelines and metadata schema. So metadata for us in the community is super and crucially important. The quality and accuracy, we have this ingestion into OpenAI graph. Most of the data sources, they come through validation, and we have a brokering service. And then the completeness is how do we complete the metadata with semantics that the community is aware of, but they just don't bother to put in the metadata, or there is no place to put in the metadata. The supply chain, I will go again very briefly, is to combine data from global research ecosystem of more than 10K data sources, different records. I will not go into the details, but again, metadata is super important. The AI-driven data infrastructure. So we have now 13 services and toolkits within our workflow. And then what is important is who is the recipient of that. So there are many third-party services, SMEs using the research data to do evaluation of funding and national infrastructures, EOSC as a discovery service. We use it in OpenAI, in the OpenAI monitor dashboards for institutions and funders. We use it for research community in the Connect. We use it in different settings, like for Intelcom, which is a project using the OpenAI graph for science, technology, and innovation observatory in Europe. So the Commission is really interested in that. We use it as a direct connection to the European Commission portal. And also, we use it for cases like today. I was not here because I was giving a presentation about the connection that we will do to the global climate hub. They want to use it as an science, technology, and innovation for their observatory. The physical infrastructure, okay, some of these numbers are not here. This is what I tried. These were the versions, Jan. So this is a big infrastructure. So we have a public, in order to have the public productions, we have 49 servers, and you can see the terabytes and the gigabytes of memories and the CPUs. So I think the middle one is about, the numbers missing, is about the text and data mining, which requires much more memory and much more disk space. And the blue one is about the development production, which also requires a lot. So what I'm trying to say with this one is that it's not a trivial infrastructure. It's a big infrastructure, and it's a scholarly communication, and it's something that we need all to join efforts in order to make it work. Now, my last 2 or 3 slides, integration is in practice. So where do DMPs and SKGs come together? What Thomas presented is this is the graph from the RDA. What we have done internally in Argos is that we have from the beginning, we have linked this DMP to the funding. And now we take box by box, and we are progressing in while a researcher is doing their DMPs, they can be able to identify, for example, data sets that can be reused, license from, because we have them on the graph, and costs, for example, we can give them indications from the cost for publications on publications from the open APC. So this is the mentality that we're moving forwards, and I think this is the mentality all of the DMPs are moving or should be moving forward. Now, in a recent one, we have an integration with RawHub with the Reliance project. So RawHub is the RawCrate or something research object hub, a research object, and they are, in my understanding, it's a way that you can package workflows. and see to see how they can be used for reproducibility. So these are now integrated in Argos, and also we are using the RSpace integration for pre-filling, linking, and publishing information between platforms. So a lot is coming forward, and I think what Thomas said about the DMPs being in the center is crucial for not only for the researchers, but also for the research infrastructures, is because they can have this as an invaluable tool is to guide the researchers to the right directions. And then I have one, one thing is, what is in the center? Is the DMP in the center, or is the knowledge graph in the center? There is, I think they are equally important. I don't know which is more important than the other, but this is something that we need to consider. And then for Argos, for example, in the integrations that we're doing is on the national instances, is the Polish supercomputing center is using them to connect to the raw hubs. Institutional repositories in Portugal are connecting it to their Dataverse and to the national CRIS systems. Consortia like Madrono Consortia, which is the library consortium in Spain, they are using it and they have already installed it. So what they actually did is they had DMPs already, they exported them from their own system, they importing in Argos. Now Argos is the national for universities, and we have quite a few in the pipeline, mainly from national infrastructures. And I think this gives you an idea where we're going, and I'm sorry if I took more time, but it was too much to tell. But this is the idea, I think, where we're going into, where we, not where we should be going, but where we are going already.
Thank you, Natalia. Your last sentences are a good introduction to the panel discussion. I would like to start the panel discussion now and ask the colleagues who are online to open their cameras, and so that we... Thanks, Marcus and Larry and Gabriella. I have three major issues I would like to raise, and I kindly ask you to for your contribution in answering that. Of course, if you want then to add some other points of view, please do it. They're welcome. So we have seen in this last and fourth closing session, also focusing on data, that we need to be interoperable on a global scale. This is the first statement. So the global scale is very important, and this global scale is characterized by data spaces, which could be at the regional level, could be vertical in one or more disciplines, or from the beginning on global. Then we have the issue of the quality of the content and the quality of the structure. So the quality of the content, usually the researchers, they are the person or the content provider are the persons who should pay attention to the content. Now it's required also to pay attention to the structure. Why? Because we are entering a phase where the virtual researcher is needed. So virtual research environments are becoming more important. And we are now entering with the virtual researcher environments, the field of the machines. Now I will come to my three major questions. As I started to study, it was in the last century, I remarked that some colleagues were not allowed to study what they wanted to study because they did not have notions of Latin. So if you want to study medicine, you have to show that you learned Latin. If you want to study similar studies like biology and so on, you have to show you have learned Latin, because Latin was the lingua franca in research. Okay. Now, the people that at that time did not have this Latin knowledge, they had to fulfill some further studies in order to be admitted to the university. And then they were admitted and they realized that whatever they do, it's not in the local language, but it's in English. So they realized they also had to learn English. It's another language. Because it seemed that the language of research is English. Now, in the virtual researcher, in environments, the language is neither Latin nor English nor French nor Spanish. It's the machine language. Now, my first consideration and question to you all is how can we then cope with this? So the machine language is the language which is needed now. Everything should be machine actionable. So we need machine language. The entities who are governing the machine languages, they will govern the internet. They will govern research, the findability of research, the discoverability of research, the interoperability of research. How can we, or your recommendation, initiate a discussion, a good discussion with the lawmakers and the decision-making persons at the rectorates level in order to maybe not forget, but forget Latin and English, but to go into this new world, machine language. Who should learn this and who should practice this? So Larry, you started with the fair digital object on a global scale. What could be your suggestion to this question?
Well, I have a couple of reactions to that, Paolo, and I have the advantage of I heard this idea from you a little earlier, and I gave it some thought, although I did not respond. As probably the oldest person on this panel, certainly one who learned very many different machine languages over the years, I'd like to point out that machine language has simplified considerably over the decades. Hardly anyone learns the low-level assembly language anymore. We kept learning higher and higher levels of language, and I think that is our goal. I think we want, to the degree possible, the scientists themselves, the researchers themselves, to be able to talk to digital objects and manipulate data out on the network as easily today as they would spreadsheets. So a lot of disciplines use spreadsheets because they fit the scientific mindset. They're a matrix and so on. I would like that to turn into a language, a fairly simple language, in which I can address an object by its identifier, ask it what it can do for me, and respond appropriately without worrying about what machine language was made to put it together, what database it has underneath it, how it was structured. And again, that seems to me to be a goal, because it will not be structured the same way some decades or more from now.
Thanks, Larry. Marcus?
Yeah, so I would second that point by Larry. So programming has become easier. Python is not assembly, indeed. And maybe I could add that I also think while knowing one of these languages, be it R, Python, or Julia, or Go, is useful for science, I think a lot can be or should be then taken over by the infrastructure. I don't think that every researcher needs to do, how to make things machine actionable, interoperable, reusable. So I think once we have a programmable environment, it's exactly the machines who should implement all that logic, not the researcher. So again, a little bit of programming is useful, but also, for instance, what I demonstrated a little bit in my slides, a lot of that ensuring that things are machine actionable can be implemented in the infrastructure and is not of concern to researchers.
Many thanks, Marcus. Gabriela, do you want to add some your point of view?
Yes, thank you. Yeah, I think interoperability is key, and obviously machine readability, actionability is key. Yeah, from the infrastructure perspective, obviously I represent an organization that provides infrastructure. This is also crucial to our principles, and that's why organizations like DataCite, ORCID, Crossref provide open APIs, open metadata. Also, we provide documentation, engage actively with the community to promote these efforts to make sure the community moves in this direction.
Many thanks. Now on the panel here.
You were asking, what do students need to learn? I think one of the most important things is every graduate student, if not students in primary or secondary schools, need to learn about the limitations of all these systems. Well, you need to learn that ChatGPT is sometimes talking nonsense. You need to know what the limitations, or learn how to distinguish the limitations of specific data sets. We did just an experiment, or actually Dave Carlson did an experiment with some people in the US, that a group of students did the peer review of a data set. So if they learn to distinguish what are the problems with data, that's very important. And then if every student, if every graduate, if every PhD researcher has learned these basics, there maybe need to be 1 in 10 researchers need to be a data scientist who knows more about programming, knows more about statistics, depending on the discipline. But there should be.
I think so I agree with both what you said and Marcus. So it should be the machine language should be mainly at the infrastructure level, for sure. Okay, then I agree with you. Not everyone can become a data scientist, because they should know the basics and the data science. But also please think about at least I have this watch, and I can say, hey Siri, do this. I hope it's not going to wake up now. But what we see is we see the graph, the biggest graph, which is Google, and then we see a lot of querying based on natural language, based on language. So you see a set of infrastructure at the bottom where it's able to translate this. And this is something, if we have our vision and the sky is the limit, we can do that. So I'm not sure why now everyone needs to understand this machine language, okay? And then also, please don't forget that it's not about what we're building, especially on the knowledge graphs. It's not only about researchers. It's used by non-researchers. So I think what I would like to say is that Marcus got it right. For sure, everyone who's building infrastructure should know this language. Then from researchers, they should know a good part, but not in every detail. And then there is a small part that they should know this data science.
Okay, thank you, Natalia. We'll come back to your last sentence, Tomasz.
So I understood your question basically that when should we start teaching these things and how can we influence the decision makers? And my answer was, yes, it's not specific to only research infrastructures, but in general, the society. Where do we start teaching the digital skills and this digital literacy? So the question is, do we want to teach kids at school how to name a file correctly and not to put it on the desktop or not? Or what is two-factor authentication that they will need for authenticating into the bank? And I think this kind of literacy then contributes to being a good researcher in the future. I was at school trained as a monkey to do spreadsheets. This is what we did in the 7th grade. So I know now how to use the spreadsheets, and I'm not questioning that this tool was useful or not. Of course, they could have taught me different things, but this was the state of the art at that time. And we have the current state of the art. And of course, we cannot teach every kid at school how to program in Python. It doesn't make sense, but they should know that this is a skill they will require in the future if they go to, for example, do studies in biology or chemistry. Because when I was going for studies as a kid, I thought if I want to do coding, I go for the IT. I had no idea that in the biology, you also need IT skills. So giving this heads up to the kids. And last but not least, I think one example of teaching skills is also at the universities, because I can give an example from Vienna. We are now working on a curriculum offered by the Faculty of Informatics to all other students of all other faculties to get the basic digital skills in data management, data stewardship principles, but also, explaining them what is a file format, how can you handle data, how to use Git, so that all those who went to study everything else in computer science can catch up with the recent developments and can benefit from that. So this is maybe a way to talk to rectorates.
So thank you for your answers. I'd like to state just a reaction on what has been said, that a part of these statements are seen from the point of view of discoverability. There is another point of view, which is the point of view of the production. At the moment we produce the data, we should also think on the discoverability, and that's where the problems then, or the challenges starts. The point, the moment where we start the production, and this is the moment where we should start then to look at the thinking from the end, the discoverability.
Part of the research into the infrastructure.
From your point of view, is a part of the infrastructures. Okay, I started with this discussion on the language because the fair digital object, for example, just to make an example, is conceived from another point of view like a morpheme in language. The more the morphemes are compliant with the rules of the language, the better the language will then function, and therefore started with the language. Now, if we take for granted that whatever you have said now it's correct, why is it so difficult to introduce DMP in the institutions, the researchers? Why do we encounter so many difficulties on this? If we work in this environment, we notice it on a daily basis. DMPs were only introduced at the moment that the funders wanted them, although everybody said, wow, it's logic, we need it. So please, Hans.
Yeah, I'm urged to say, well, be careful to base all your stakes on the correctness of DMPs, because scientists don't get a reward actually for making them correct. They're making, they get a reward if they do them nicely, so that they get funding for it. But this must not be the truth, or it need not be correct. So I can only say from experience with the latest big expedition of Polarstern, 600 people, 20 countries, 150 million euros logistics cost, that scientists from all these countries didn't know how much data they would produce on board before the expedition. We tried to extract that from that by asking, not just giving them a template. We asked them actively for 2 years. They didn't say, they couldn't say. So we just installed 700 terabytes, I think, or was it petabytes? Petabytes, yes, 700 terabytes of storage on board because we couldn't send spare parts to the Arctic, to the pole. Without exactly knowing whether that would be enough or way too much or whatever. They couldn't say. And the data policy was actually finished one day before the ship set sail in Tromsø. So
So before you take the mic, just a clarification, we are not talking about DMP. DMP is just a vehicle for the machine actionability, just an instrument, just an example. It's about machine actionability. So please.
Okay, so I will respond to you and then to you. So I think what you are describing, I wouldn't put my trust on the existing DMPs, okay? But the question is, where do we want to go? Starting from the existing DMPs, and the vision is, can we turn this DMP planning into DMP management? That would be the vision, okay? And I think we're going slowly there. If we're putting, you know, if we make it easy for people to plan, and then we link it to the SKGs, and we get the information, we link it to the repositories, then this is going to be a true living by itself, not by, you know, living by requiring people to put the, so this is, again, you know, we're not there yet. And to you is that I think now that the DMPs is that they are transitioning to something else, to a new tool. I think we will see, first of all, we need to get them to be easy, okay? Now they are a burden. Let's be honest. If, you know, in every project that we get in open air, we're trying to find who's going to do the DMP, who's going to do the DMP, because this is, you know, a contractual agreement, it's a burden. But once you have this tool that, you know, you make the effort on configuring at the beginning, and you see that the tool is helping you in your progress report, in your whatever, then you may want to do it. But this is my...
Just as a quick reference to your example, you said that you eventually decided to install these 700 terabytes. So you made the decision and not the researcher, and you should have a right to update the DMP to reflect the reality. So as I said, it's always the responsibility of a researcher now. And if we include other stakeholders like you, and we document your decision, then the DMP can have the quality because it will be up to date based on your decision. And what Paolo said, I agree that currently we don't reuse the information from the systems we have. I think this would be the incentive for the researchers to do machine actionability digital objects if we would ask them things once only. So if I, for example, I uploaded my publication to a data repository, a dataset to a data repository, I got a PID. With this PID, I want to give it to my university, funder, DMP, and everyone. And please don't ask me to type all the information again. Since I'm asked to type all this information again, I don't see any incentives in doing some of the actions. Yeah. So I think this knowledge graphs, everything we do to connect the systems to facilitate reuse is a way to create incentive for the researchers. Hopefully.
So just ask for completion the 3 colleagues who are online. So Larry, Gabriella, and Marcus, do you want to add something?
Sure. So two small comments. One, the technology is usually the easy part. The social aspect is always harder. The notion of having to get the incentives right is correct. The best you can do with the technology is make it simple and get it out of the way of the human activities. And the second thing is the closer to the source, the better. This has been in terms of metadata and information related to the research activities and so on. This has been the case for a long time before we started talking about the machine actionability. But it is especially true for this area.
Okay, thanks, Larry. Marcus or Gabriella? Or Marcus and Gabriella?
Yeah, so I think most of it has been said, right? I completely agree. So I see the problem of planning everything in detail upfront. So not knowing that you're producing 500 terabytes or 1 petabyte. I myself, as a researcher, I don't know upfront at the beginning exactly every single detail and the columns of my data sheets. And how are we going to name them? So I think that's just the nature of science also. We are not building cars according to a well-described plan. Often it's explorative and then you don't exactly know what you're going to produce. So yes, management and also kind of evolution. I think an evolving document. I think Natalia has mentioned this. I would agree with this. And in the end, so in virtual research environments, I think the update should also go automatically. So I don't see why researchers need to then update every single piece in the management, in the plan. In a virtual research environment, the system should know I'm needing more data. I'm updating the plan or the management document accordingly, or I have a more data set, or that data set has an additional column or whatever. So this is all known, and in an interoperable infrastructure, again, it's not the researcher who has to manage and maintain this stuff.
Gabriella?
Yes, I also agreed with what most of you have said. I personally see the question of DMPs and interoperability in the framework of open science, and obviously the road to open is never complete. So right now we're discussing about DMPs, but probably next year we'll talk about pre-registration reports or some other elements that still needs to be included as part of the workflow and make more interoperable. And fully agree with Marcus and Thomas that open science is the philosophy, but we need to put incentives to researchers, and this is through system integrations and more interoperability and automated exchange, so that we make it easier for them to apply these principles.
Thank you. I'm now focusing on the title of this session. So it was interlinking and interaction between data, publication, and PIDs. And I have two questions. I'd like to pose them both simultaneously, and I ask you for a reaction on this. So the first question or the first issue is if we look at on how we could implement these at our research institutions, then we notice that we need policies to be implemented then, and these policies are concerning research data management. And these policies are then related to services and infrastructures in a secondary way. But in these RDM policies, they contain a sentence. In this sentence, there is a reference to the machine actionability of what researchers do. How do you see some possibilities to send some messages to the policymakers at the research institutions on how to change these policies in order to make it realizable what we have said today? How could this recommendation be? And the second question is what you have presented. Each presentation should also be linked to the upcoming data spaces. In your activities, how do you see the possibility to link your activities to the upcoming data spaces the way they were presented this afternoon? So who wants to start?
May I be so crude to answer your last question? I have no idea. I have no idea how a publication or a publisher could link to all these data spaces, even though many publications address issues which are located in one of these different spaces. For example, we have lately many submissions with or about land use and as it affects the climate. So there would be, of course, agriculture, there would be environment and whatnot, and of course EOSC as a horizontal data space. So I have no idea how the publisher, how Copernicus, should in daily business address this question. No.
Before I give the floor to Natalia, we have heard today that the French ministry is heavily involved in the realization of the first European common data space, which is health, and we know who are the people. So Natalia.
Okay, so the first, I will try to first say a few words about your first question. I think is in the policies, we have model policies for institutions. And the only thing that you can put in the policy is like when you're depositing something or when you're using something, you need to make sure that this allows protocol A, B, and C for machine actionability. And I think this can be only a soft mandate. But the policy inside the institution can say, okay, I will buy or I will use or I will deploy only tools that are doing that. So for example, for data management plan tools, there are some that don't have this machine actionability, so I wouldn't promote them. But there are some that do have it, so I would use them. Now, for data spaces, it's peculiar. So DMPs, I'm not sure that they have they're not thinking about DMPs, because think about data spaces, it's mostly commercial or non-research data that is being shared. And they're using the architecture they're using there from the International Data Spaces architecture, which is mainly the data is accessed via services. So these services, so that means is that these services, even if the data doesn't have this machine actionability, that the services themselves will make sure that they somehow transpose or transmit this machine actionability. For health data spaces, for example, you have a bunch of layer of services from anonymization to, even to synthetic data sets, everything that it's all the access is via services.
I can only say I agree with the things that has been said. So in general, I think we have this change of paradigms from time to time. So sometimes so in the 70s, we had one computer where everyone was working, and then we went to people downloading data on their local computers to do computations. And now we are again using the services. And the thing is that if you have a controlled service in which you can track provenance, which you know who is the user, how is using the data, you can do a lot of things automatically and can improve automatic collection of data. As long as we do the collection, the processing of data on the laptops when people download the data sets, then we lose control of what's going there, and then we have to depend on what researchers will provide you very often manually. Yeah? But just as to add to what Natalia said.
Gabriela, Marcus, and Larry, please.
I would reply to both questions with the same answer. And I would say the key is to use infrastructure already in place. We've seen a lot of good examples today of infrastructures that are already in place, that are already supporting and driven by global communities. So I think that's very important to build on existing infrastructure that already works, that already is making progress, and also to build on existing communities that are already engaged and driving those infrastructures.
So from my side, maybe on a technical, I'm not sure how to inform the or what are the take-home messages for policymakers. I leave this to the seniors among the panelists. But from a technical perspective, I think the technology we need to do this data spaces is available. I think to boil it down to one key ingredient, I think is shared identifiers. So ensuring that when you talk about the same thing, you actually refer to it with the same identifier. That would help across infrastructures, of course, to ensure the interoperability. Linked data is showing the way, although it's more complicated than that. I think in the end, in practical infrastructures, you need to version statements, you need to be able to track provenance and state all kinds of additional annotations. So it's not easy to get this infrastructure to a certain maturity that we need in science. But I think most of the technology that we need, or indeed probably all that we need, is available. It's just a matter of plugging things together the right way.
Okay. I think one answer to the question is to be stubborn. I had the job of convincing people that persistent identifiers were worth the effort. I wasn't always received gratefully with this. You have to do more for the benefit of the future. That wasn't popular. So keep at it, be stubborn, sell a vision. And secondly, rough consensus and running code. That's my internet background, but demonstrate that there are benefits here. Show that there are benefits. One of the things that drove TCP/IP adoption was something called Interop, which is a conference, physical conference, where you brought your devices and see if they work together. I think we need a virtual version of Interop, where you bring your data and your management plans and your articles and so on, and see if it works together. And can you develop an autonomous agent that can navigate all that stuff, demonstrate it, show that you can do things with this approach, this machine actionability approach, that you can't do now.
Thank you, Larry. Thank you, Marcus, Gabriella, Larry, for joining us virtually and contributing to this session. Hans, Thomas, and Natalia, thank you very much also to you. And to all of us, thank you for having participated. I'd like to close with these words this session, and officially also this e-IRG workshop. And I will now give the floor for the last statement to Jan Gruntorad as organizer of this event. Jan.
Thank you. Well, I would like to thank you for your very active participation to the workshop. We have learned very interesting topics, and there were a lot of interesting lectures and ideas and discussion. They believe they will contribute to resolving very complex environment of the e-infrastructure we are facing these days, with the difficulties of the high energy prices and let's say economic difficulties and things like that. So I believe it was very useful. Even we can share best practice on this topic. I would like also thanks my colleague who arranged the catering and registration of the workshop, and of course the technical part. I believe it worked pretty well. So many thanks for that. And to the e-IRG delegate, I would like to remind there is a dinner taking place at 7 p.m. You should receive by email instruction how to get there. We have chosen a restaurant in a center of Prague in order you can feel the Christmas atmosphere in the center of Prague. But please look at the map you have received, because to find the restaurant is quite a challenge. Frankly speaking, even I have difficulties to find it, because the address it's the street Celnici, but actually it's not on the street, it's on the square. So please took the right exits of the metro, because there are several exits. So please have a look at the map, which exit to take. And the restaurant is really not in the streets, in the square. but I believe you will find it if you know this topic. So don't go at the street Silnici and go at the first corner to the right, and you will reach the restaurants. And by metro, it's 20 to 25 minutes if you go from here. So I believe that I will meet you there. So thank you again for the very, let's say, fruitful workshop. And I believe to see you again one day again in Prague. Thank you.